Indeterminate form of other types. Our objective is to find the limit of an indeterminate form of the type 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, or infinity to the 0. Remember that L'Hopital's rule can only be used for indeterminate forms of the type 0 over 0 or infinity over infinity. Therefore, we must rewrite indeterminate forms of the other types, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, infinity to the 0, into the form where we can use L'Hopital's rule, 0 over 0 or infinity over infinity, before using L'Hopital's rule to find the limit. Let's look at some examples. Identify each expression as an indeterminate form of type 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, or infinity to the 0. Then find the limit. Limit as x approaches 0 from the right of x times cotangent x. Cotangent x, if you recall, is a graph that looks like this. Why is that helpful to remember? Well, if x is approaching 0 from the right, and this is the y-axis, so this is where 0 is, we notice that from the right, the graph is increasing without bound. So using direct substitution, the limit of x is 0, and the limit of cotangent x is infinity. So I have 0 times infinity. That's one of my other types of indeterminate forms. I can't use L'Hopital's rule yet. I must rewrite it, if I can, into the 0 over 0 or infinity over infinity form. Then I can use L'Hopital's rule. So let's look at how we can do that with this function. Limit as x approaches 0 from the right. I can multiply by a number and divide by its reciprocal. Same with expressions. So I'm going to say, instead of x times cotangent x, I'm going to say x divided by the reciprocal of cotangent x, which is 1 over cotangent x. That's easier to think of as tangent of x. So again, we'll rewrite this limit as x approaches 0 from the right of x over tangent x. Now when I plug in 0, I have 0 in the numerator, tangent 0 in the denominator, so again 0 over 0. Now it's an indeterminate form where I can use L'Hopital's rule. So let's apply that. The limit as x approaches 0 from the right, derivative of the numerator is 1. The derivative of the denominator, tangent x, is secant squared x. Using my direct substitution, I have 1 over secant squared 0, which makes 1 over 1, which is 1. That is a valid limit. I have my answer. Number 2, the limit as x approaches 0 from the right of x times natural log x. Let's recall what the graph of y equals natural log x looks like. And notice, as x approaches 0 from the right, where the graph is headed, negative infinity. So using our direct substitution, the limit of x as x approaches 0 is 0, and the limit of natural log of x as x approaches 0 from the right is negative infinity. Whether it's positive or negative infinity, this is still one of the indeterminate forms of the other types. So we try to rearrange this to get the indeterminate form of the type where we can use L'Hopital's rule. Let's rewrite this as the limit as x approaches 0 from the right of natural log x divided by, instead of times, x, it'll be divided by the reciprocal of x, 1 over x. So the limit as x approaches 0 from the right of natural log x is negative infinity, as we discussed previously. And when I plug 0 into x, that makes the denominator get increasingly small while the numerator stays the same. So that's going to go to infinity. we have the form infinity over infinity, and therefore we can use L'Hopital's rule. The derivative of natural log x, the numerator, is 1 over x, and the derivative of the denominator, 1 over x, is negative 1 over x squared. Now I do prefer to simplify this before I try to use direct substitution. It's just easier. And I get negative x squared over x, which is the same as negative x plugging in 0 yields a valid limit of 0. Three, limit as x approaches 0 from the right of 1 over x minus 1 over sine x. Plugging in 0, 1 over a number getting very small becomes very big, so the limit of 1 over x is infinity. Sine of 0 also is approaching 0, so 1 stays 1 while the denominator gets small, and therefore this limit is also infinity, and we end up with infinity minus infinity, another indeterminate form of the other type. And I need to try to get an indeterminate form of a type where I can use L'Hopital's rule, 0 over 0 or infinity over infinity. To do that, I want one quotient here. So I'm going to work on getting a common denominator. I can multiply by each other's denominators. This one will get multiplied by x over x, and this one will get multiplied by sine x over sine x. So I end up with sine x minus x over the common denominator x times sine x. And this is my new limit, x approaching 0 from the right. We use direct substitution. Sine of 0 minus 0 makes 0, and 0 times sine of 0 makes 0. Now I have the indeterminate form of the type where I can use L'Hopital's rule. So let's begin taking our derivatives of each side of the fraction. The derivative of sine x is cosine x, the derivative of x is 1, and for the denominator I need the product rule. So I have x times the derivative of sine x, which is cosine x, plus sine x times the derivative of x, which is 1. Direct substitution into the numerator, cosine of 0 minus 1 over 0 times cosine 0 plus sine 0. This is 1. 1 minus 1 is 0, and in the denominator, 0 again. But because I have the indeterminate form of the type 0 over 0, I can once again do L'Hopital's rule. The derivative of cosine x, negative sine x. The derivative of 1 is 0. And now I head to the denominator. For this part again, I need a product rule. X times the derivative of cosine x is x times negative sine x plus cosine x times the derivative of x, which is 1, so plus cosine x. That's my product rule for this product, plus the derivative of sine x, which is cosine x. All of that for my denominator. Now I try my direct substitution. Negative sine of 0 over negative 0 sine 0 plus cosine 0 plus cosine 0. Sine of 0 is 0. This part, 0 plus cosine 0 is 1 plus 1. So I have 0 divided by 2, which does equal a valid number, 0. I have now found my limit. Number 4, the limit as x approaches 0 from the right of 1 plus 2x to the power of 1 over x. Using direct substitution, 1 plus 2 times 0 to the 1 over 0. Inside the parentheses here, I have 1 plus 0, which is 1. And when a fraction has a denominator that gets smaller and smaller, that fraction is headed to infinity. So the exponent infinity. This is another indeterminate form of the other type, 1 to the infinity. For this one, we're going to use the strategy where we can get the exponent to get out of that spot in the exponent. So we're going to let y equal that function that we're taking the limit of. Y equals 1 plus 2x to the 1 over x power. And to get that out of the exponent, we take the natural log of both sides. Natural log of y equals natural log of 1 plus 2x to the 1 over x. That way we can use our property of natural log that says that exponent can come in front to be a coefficient. So natural log of y equals 1 over x times natural log of 1 plus 2x. Now instead of taking the limit of that, let's take the limit of this. Limit as x approaches 0 from the right of 1 over x times natural log of 1 plus 2x. This is the same as looking at it like one quotient, natural log of 1 plus 2x over x. What happens when we try direct substitution? 0 into here makes natural log of 1 over 0, and natural log of 1 is 0, so we get 0 over 0, which is an indeterminate form where we can use L'Hopital's rule. So let's do that. The limit as x approaches 0 from the right. Looking at the quotient, I want to take the derivative of the numerator. Just focusing on the numerator, the derivative is 1 over 1 plus 2x times, using my chain rule, the derivative of the inside, which is 2. And now the derivative of the denominator, 1. I'm going to simplify this, so I have the limit as x approaches 0 from the right of 2 over 1 plus 2x. Now when I use direct substitution and plug my 0 in there, I have 2 over 1 plus 2 times 0, which is 2 over 1, which is 2. Now remember, we rewrote what y equals, and we took the limit of something else. So we have to think back to what we did. The limit as x approaches 0 from the right of natural log of y is what we did, and that gave us 2. We have to undo the natural log. So think of it like if we had this expression, to undo the natural log, we would exponentiate both sides, e to the natural log y and e to the 2, so that that inverse property leaves us with y equals e to the 2. Similarly, we do that with this limit expression, so that the limit as x approaches 0 from the right of y equals e to the 2, or e squared. Thanks for watching.